Okay, good morning, everyone. Welcome to the GIST Sea Level Rise seminar. We're very glad to have Dr. Laura Larocca, who is an assistant professor in the School of Ocean Futures at Arizona State University. Dr. Larocca is a climate scientist whose research focuses on understanding past and contemporary climate change and its impact on Earth systems, with an emphasis on the cryosphere. And her work employs a variety of approaches, including the use of sediment and other natural archives, historical and remotely sensed observations, and geospatial tools and modeling. Prior to her current position, Dr. Larocca was a NOAA Climate and Global Change postdoctoral fellow at Northern Arizona University. And Dr. Larocca earned her PhD from the Department of Earth and Planetary Sciences at Northwestern University, and her MS from the Department of Earth and Atmospheric Sciences at the City College of New York, and her BFA at the Steinhardt School of Culture Education and Human Development at New York University. So she will be speaking today on the topic Greenland-wide accelerated retreat of peripheral glaciers in the 21st century. Welcome.
Well, thanks, Patrick, for that introduction, and thanks for the invitation to speak this morning. It's my pleasure to talk to the NASA GIST community. So like you mentioned, today I'll talk about some recent work, which first aimed to document the response of Greenland's peripheral glaciers to climate change over more than a century, and second, to place the recent retreat of these glaciers over the last few decades into that century-long context for the first time. So we were really interested in getting at the question, how unusual or unprecedented are these recent changes in these smaller ice masses that dot the land around the Greenland ice sheet. So to go about answering this question, we used a few really unique observational data sets, one of which is a set of historical Danish air photos. So the background photo here shows some of the Danish pilots in the open cockpit plane that they used to collect photos of Greenland in the 20th century. And the aerial photos collected during these mapping expeditions of the coastline really represent the only robust and widespread observations of 20th century glacier change that we have for the vast island of Greenland. So before I get into the work, I'd just like to first acknowledge all my co-authors. So I started this project when I was still a PhD student at Northwestern University with Yarrow Axford. I also worked with Anders Bjork from University of Copenhagen. He was on my committee and also pioneered the use of these air photos. I'd like to also acknowledge Max Twinningward. He led the data collection in northern Greenland, and also Avril Schweizenberg and Jason Briner from University at Buffalo, who led the data collection in western Greenland, and also others from University of Copenhagen and the Geological Survey of Denmark. So this study really wouldn't have been possible without this international collaborative effort and access to the historical images at the Danish National Archives. There was also hundreds of hours of analog photo processing by myself and also several of the co-authors that you see here. So it was really a true collaborative effort, and the work was more than 5 years in the making. So I'm sure everyone here is aware over the past several decades, temperatures in the Arctic have increased substantially more than global temperature. So the plot here shows annual mean temperature anomalies in the Arctic, these darker colors, and globally, the lighter colors between 1950 and 2021 derived from these four observational data sets. And these data show that the Arctic has warmed almost 4 times faster than the global average from 1979 onwards, a phenomenon often referred to as Arctic amplification. So in response to these increases in temperatures, of course, glaciers globally are shrinking and losing mass. This figure shows regional and global mass change rate with time series of mean surface elevation change rates for glaciers in the 19 first order regions of the Randolph Glacier Inventory. And in the first 2 decades of the 21st century, Greenland's glaciers specifically lost mass at a rate of about minus 35 gigatons per year, and that rate was only outpaced by Alaskan glaciers and ice caps. So mass loss from glaciers and ice sheets are contributing to global sea level rise. And although they're much smaller in area and volume as compared to the Greenland ice sheet, glaciers peripheral to the Greenland ice sheet are actually important contributors to global sea level rise. So as shown here on the map on the right and in the table here from a recent study by Kahn et al., glaciers peripheral to the Greenland ice sheet constitute a pretty small portion of Greenland's total glaciated area, just about 4%, but they now contribute a disproportionately large portion of the island's current ice loss, so about 14% of that total loss. So the global retreat of glaciers is a prominent indicator of the ongoing changes that are occurring, ongoing anthropogenic warming, yet our ability to evaluate contemporary glacier loss within an extended temporal context has remained pretty limited, and that's because observations of glacier change before the satellite era are pretty sparse. So this is owed to their remote and logistically challenging settings, and so direct measurements on Greenland's glaciers are even more sparse. So for example, among Greenland's roughly 20,000 glaciers, just one glacier has ongoing mass balance measurements, and those begin in the mid-1990s. So this not only limits our understanding of glacier sensitivity to climate change, but also our understanding of the degree of unusualness of these very recent and rapid changes that we're seeing. So in recent years, historical data sets have proven a pretty valuable resource in filling some of these observational gaps. So for example, rediscovered and declassified photos from aerial campaigns and early satellite missions have been used. And I'll talk a little bit more about these 2 data sets that were used in our compilation in the next few slides. The Corona satellite mission and imagery from Danish aerial mapping expeditions. So the Corona program was a series of American satellites produced by the Central Intelligence Agency, and they were used for photographic surveillance of the Soviet Union and other areas between 1959 and 1972. And this was a really unique satellite because film was actually retrieved from orbit using a re-entry capsule that was designed by General Electric. So it separated from the satellite and fell to Earth. And once it re-entered Earth's atmosphere, parachutes deployed, and the capsule was intended to be caught in midair by a passing airplane, or it could land at sea. If it landed at sea, there was a salt plug in the base that would dissolve after a few days, that would allow the capsule to sink if it wasn't picked up by the US Navy. So these images were declassified in the 1990s, and they've been pretty widely used for historical Earth observations. So now I'll just talk a little bit about the archive of Danish air photos. So in the early 20th century, there were several expeditions launched in Greenland to produce new geographical maps, or in many instances to map the coastline of Greenland for the first time. So these photos here show some of the Danish pilots and the open cockpit planes that they used to survey East Greenland in 1932. These pilots dealt with pretty tough conditions, cold, high altitude conditions. As you can see, they're wearing polar bear fur jackets. They flew these planes at about 4,000 meters altitude to clear Greenland's mountainous terrain. So they collected all these photographs, and then after the initial use of them, they were actually classified and not generally accessible. So they laid forgotten in a 17th century fortress outside Copenhagen until about 15 years ago, when my co-author and colleague Anders Bjork first came across them. And Anders sensed a pretty unique opportunity here to observe 20th century changes in Greenland's glaciers at high spatial resolution, but it took him many years to sift through these boxes filled with thousands of light-sensitive negatives and to work out like which photos might be useful for scientific questions. So as he extended his search for these air photos, he did come across many more images taken during Danish and US Greenland aerial surveys from the 1940s all the way through to the 1970s. And so together, the collection includes more than 200,000 aerial photos of the coast of Greenland. And you can see all of the flight lines here in these blue lines from all of these decades. And so these photos capture the state of Greenland's peripheral glaciers during a period when quantitative observations and measurements are largely absent. So there were also additional Danish mapping expeditions carried out between 1978 and 1987. So there are additional set of about 3,500 vertical photos, and these photos were recently used to produce a high-resolution orthophotograph. And we use this as our reference data set, which I'll talk a little bit more about in a bit. And so together, all of these collections really provide us with invaluable pre-satellite era observations, and they allowed us to extend the duration of the observational record of Greenland's peripheral glaciers. So I just wanted to give a little bit of context in how these photographs were used prior to our work. So these historical data were first used in a 2012 study by Anders Bjork that documented the response of about 130 glaciers to climate change in Southeast Greenland over 80 years. And they found relatively high retreat during a period of warming in the 1930s and also in the 2000s. They also showed that many land terminating glaciers underwent a more rapid retreat in the 1930s than in the 2000s, whereas marine terminating glaciers retreated more rapidly during the recent warming period. In 2018, Anders and others used these historical aerial surveys and the SPY satellite imagery, along with remote sensing products, to map the length fluctuations of an additional 350 peripheral glaciers and ice caps in East and West Greenland since about 1890. And they showed that regional changes in ice volume as reflected by glacier length are related to changes in precipitation associated with the North Atlantic Oscillation. So they found that positive phases of the NAO increase accumulation and thereby glacier growth in the eastern periphery of Greenland, whereas the opposite effects were observed in the western periphery. They also suggested that with projected trends toward positive NAO in the future, that these eastern peripheral glaciers might remain relatively stable, while the western peripheral glaciers will continue to diminish. And then finally, a pretty recent study from 2020 used these historical data to estimate ice mass change between 1880 and 2012 for Greenland's three largest outlet glaciers, Jakobshavn, Kangerlussuaq, and Helheim. And this study finds that the amount of ice lost during this 130-year period is pretty comparable to the projected mass loss by 2100 under the worst case scenario from the IPCC, where the temperature change is estimated to be about 4 times larger than that which has taken place since 1880. And so one of the key takeaways from the study was that it strongly suggests that these future projections of mass loss from these three glaciers are likely severely underestimated, and that their contribution to sea level rise could far exceed that worst case scenario set out by the IPCC. So I think this study really clearly demonstrates the importance of these longer term observations in improving our understanding of glacier sensitivity to changes in climate. So just to summarize some of the motivations here for the work. So these long-term records of glacier fluctuations provide first, a context for these very recent changes, and second, they provide us with constraints for future changes. And I've shown that a limited number of glaciers have these 20th century observations and only in a few regions of Greenland. So we decided that what was ultimately needed was a Greenland-wide view. So we took this opportunity to extend the limited time frame of glaciers and ice caps across all major regions of Greenland. So I'll just summarize the overall project here before I get into the details. So combined with satellite observations, we used the underutilized archive of aerial photographs to document the evolution of more than 1,000 individual glaciers over 130 years. So specifically, we mapped the ice front positions of 821 glaciers in South, North, and West Greenland. And we also extended to present an additional 364 records of glacier length change that began in the early to mid 20th century from southeast, northwest, and northeast Greenland. So our observations cover all of Greenland's major regions, and it more than doubles the number of glaciers in Greenland with these detailed air photo-based 20th century records of length fluctuations. And importantly, this effort enabled us to contextualize the Greenland-wide magnitude of 21st century glacier change within a century-long timescale for the first time. So I'll just jump into the methods now in the next few slides. So we focused our study on glaciers that terminate on land and that are distinct from the Greenland ice sheet, so that is physically detached or dynamically disconnected. And these glaciers are fed by local precipitation and are primarily sensitive to atmospheric climate variability, and they're thought to respond to climate shifts very quickly. So here I'm just showing a schematic of all of our data sources used in our compilation and the time span that they cover. I also wanted to mention here that to further extend our records to the turn of the 20th century, we also documented ice extents based on geomorphic evidence. So for example, terminal moraines, which mark the maximum glacier extent during the Little Ice Age. And then for the air photo and satellite imagery data collection years, these were just based on the availability of quality late summer, low cloud and low snow cover imagery. So you might be wondering, why hasn't this work been done before now? So although these historical data offer invaluable insights into glacier status before the widespread use of Earth observing satellites, documenting past glacier states from these aerial imagery is quite difficult, and it requires a labor-intensive process that currently can't be automated. So the mapping that we did is a result of substantial archival work, so digitization, orthorectification, and georeferencing of thousands of these analog photographs from the Danish National Archives. So I actually went to Denmark in 2018 to scan paper copy air photos using a Canon precision scanner, and we scan these at pretty high resolution. And then here on the right, I'm just showing an example set of the overlapping 20th century historical photos that were scanned, and you could see that we selected the vertical only air photos for use. So we decided not to use the oblique photographs that require more pre-processing. So once we had all of our photos in digital form, the photos were oriented, rectified, and rectified to a standard shapefile using the image fiducials and cropped in ArcGIS. We then generated orthophotos to remove terrain distortion from each of these sets of overlapping historical images. And then all of the orthophotos were georeferenced in ArcGIS using tie points near the glacier fronts for co-registration to that 2-meter orthomosaic, which I had mentioned that we use as our reference data set. And that is what is shown in panel C here on the bottom. So the glacier fronts in the 20th century historical imagery and also in the satellite imagery were manually digitized as polylines at the transition from ablated ice to bare bedrock. And the Little Ice Age maximum extents were digitized using that high resolution orthophotograph. So this figure just shows the front retreat of an example glacier in southern Greenland between 1900 and 2021. So then to calculate the frontal change rate in meters per year, we used a couple different methods. So the first method shown in panel A here, the multi-center line method, quantifies the front change between each observation every 10 meters across the entire glacier margin. In B here, I'm showing the center line method, and this method quantifies the front change between each observation along the glacier center line. So in other words, the frontal change rate is calculated by measuring that straight line distance between point features divided by the number of years between the observations. And then lastly, in panel C here, I'm showing the method that we use to extend the data sets from the southeast, northwest, and northeast to present. So the front change in the most recent subperiod, X equals the total length change between the late 20th century observation and present, which is denoted by Y, minus the sum of the length change that occurred in the previous two subperiods, Z1 and Z2. And the frontal change rate for the most recent subperiod was calculated just by dividing that total length change X by the number of years between the final two observations. So now I'll get into some of our results. So here I'm showing the frontal change rate in meters per year over time for our 8 major regions in Greenland, and those are in these 8 different colors here. The error bars represent the combined measurement error given by the maximum digitizing uncertainty and the maximum mean error from the orthomosaic. The increased transparency here in the 6 reported post-Little Ice Age rates signify their higher uncertainty due to poor constraint on the timing of Little Ice Age deglaciation across Greenland, which I'll talk more about later on. The dashed black lines here show the mean frontal change rate across all observations in the 20th versus 21st centuries. So as you can see, over the full 130 years of observation, Greenland's land terminating glaciers have undergone pretty substantial and widespread retreat. And although we observe retreat over the full observational period, the acceleration in recession in the 21st century really stands out as distinct. So across all 8 of our regions, the mean frontal change during the 21st century is roughly double that of the 20th century. And we think this marks a major transition into a new and rapid state of downwasting. Further, despite the wide range of climate zones and glacier characteristics across Greenland, we find that this recent accelerated retreat is ubiquitous across all of the regions, including among Earth's northernmost glaciers. In addition to length change in absolute terms, we also calculated 21st century length change in relative terms. So as the percentage of length lost relative to the late 20th century length, using that common data set between regions. So we found that over the last 2 decades, South Greenland's glaciers lost about 18.5% of their total late 20th century lengths, while glaciers in the other 7 regions lost between 5 and 10% of their late 20th century lengths. Our data also suggest that recent retreat is largely unprecedented in over a century. So first, of the glaciers that we studied with at least 2 observations, 1 in each century, the highest rate of retreat on record occurred within the 21st century for 87% of them. And then second, of the 6 regions with records beginning around the turn of the 20th century, so between 1890 and 1910, which I've marked here with these stars, the regional frontal change rate in the most recent observational period is unmatched in more than a century in all but 2 of those regions, the South and the Northeast. So in the South, the post-Little Ice Age retreats retreat rates have been nearly matched by recent loss, so within error. But the major exception is the Northeast, where retreat rates in the 21st century have not yet exceeded the rate of retreat in the early 20th century or post Little Ice Age. However, we do argue that these periods, so the post-Little Ice Age period and recent, are not really directly comparable in terms of measurement uncertainty, climate, or glacier hypsometry. So first, the uncertainty in the reported post-Little Ice Age rates is higher because constraint on the timing of Little Ice Age deglaciation is pretty poor across Greenland, and glacier and ice cap front position is inferred from undated geomorphic evidence. Second, the high rates of retreat post-Little Ice Age can in part be explained due to differing glacier area elevation configurations. So for example, some glacier fronts would have been situated at much flatter and lower elevation terrain post Little Ice Age than at present. And this implies a higher sensitivity following the Little Ice Age maximum, as comparatively more glacier surface area would be exposed to ablation with a comparable rise in temperature. So I just wanted to elaborate a little bit more on that first point. So we also noted that some studies, notably those that use cosmogenic exposure dating of glacial moraines, generally suggest an earlier and variable Little Ice Age maximum timing. So in that case, an assigned age of 1900 for the timing of deglaciation in the south or 1910 in the northeast would result in artificially high retreat rates for that first observational period. So in other words, if the onset of Little Ice Age deglaciation occurred earlier than we had reported here, making our estimated rate of retreat in that earliest observational period artificially high, this would ultimately bolster our conclusion that 21st century retreat is exceptional on a century timescale. We also acknowledge that the Little Ice Age moraines are probably different in age between these individual glacier systems. And so assigning a single date to that Little Ice Age maximum or the onset of deglaciation for a large region is unrealistic. And this really imposes a difficult to quantify uncertainty on the retreat rates that use the Little Ice Age maximum as one end of the observational period. So we also assessed glacier response to changes in climate by comparing our regional frontal change rates with long-term weather station records. So some of these records begin as early as the late 1700s, and we chose 7 stations with long-term observations located closest to our regions of interest, and those are marked by the colored triangles here. So we looked at summer temperature and accumulated precipitation for the winter half year, October through March. We also looked at catchment-specific climate and surface mass balance output from the MAR regional climate model. Specifically, we extracted summer air temperature, snowfall, and surface mass balance annual sum between 1950 and 2019. MAR is forced at the boundaries with ERA5 atmospheric reanalysis, and we used the monthly mean values downscaled to 1 kilometer, and we took an average of the variables over each glacier catchment. Finally, we collected information on glacier-specific characteristics, including elevation, area, aspect, and slope from the Randolph Glacier Inventory. And we calculated a regional hypsometry using the Arctic DEM mosaic product and the glacier polygons from the Randolph Glacier inventory. So here I'm showing one of the main figures in the paper, the results of the climate and glacier front change comparison. So here in panel A, I'm showing the locations of all of the studied glaciers and the nearby DMI stations in the circles and triangles. In B, I'm showing the frontal change rate, which you've seen before in meters per year for our 8 regions. C here shows the summer temperature anomaly from the weather stations, and bars are the 10-year mean. D shows the winter half year accumulated precipitation, again from the weather stations. And then finally, E shows the regional surface mass balance anomaly from MAR, and bars are the 10-year mean of the annual sum. So overall, here we find that the regional trends in climate and surface mass balance from the regional climate model MAR agree pretty well with our frontal change rate measurements. And this confirms that Greenland's land terminating glaciers are pretty rapidly responding to climate changes via adjustment of their front positions. So for example, when we compare just the first 2 decades of the 21st century, just denoted by this dotted rectangle, we find that we find a higher rate of retreat and more negative surface mass balance in the most recent observational period compared with that of the first decade of the 21st century for glaciers here in the south, for glaciers in the north, in the southeast, in the northwest, and also in the 3 other western regions, central, west, and then our 2 southwestern regions. And then conversely, glaciers in the northeast experienced a lower retreat rate and a less negative surface mass balance anomaly in the most recent observational period compared to that of the first decade of the 21st century. So here I'm showing the surface mass balance anomaly by decade, again, colored by our 8 regions. And when zooming in here at the most recent decade alone, we see a notable divergence in both the rate of retreat and surface mass balance between glaciers in eastern and western regions of Greenland, most dramatically between the northeast, which is in this light blue color, and the southwestern regions in the yellow and olive colors. So in the eastern regions, we see a less negative surface mass balance anomaly and less retreat. And then in the western regions, we see a more negative surface mass balance anomaly and much higher retreat rates. So we looked further into the climate patterns, hoping to understand what's driving this east-west divergence. So here on the left plots, I'm showing summer temperature anomaly and snowfall anomaly by decade, again, colored by regions. And these plots show that while summer temperatures have generally increased across all regions over the past several decades, of course, with varying magnitudes of change, there is much more regional and interdecadal variability in precipitation. So here on the right plot, I'm showing the spatial trends in summer temperature and snowfall annual sum for just the 2010 to 2019 period. So here, the reds show warmer temperatures, and on the right here, the blues indicate wetter conditions or more snow. And so these data suggest that the east-west divergence probably reflects higher snowfall in East Greenland and drier conditions in West Greenland in this most recent decade. So other studies have observed a similar slowdown in mass loss from glaciers around the North Atlantic over the last 5 to 10 years. So these plots are from a recent global study which ascribed the slowdown to cooler, wetter conditions in the region over the last decade. Specifically, they find that record thinning rates of Icelandic glaciers during 2000 to 2004 were nearly halved during the 2015 to 2019 period, which coincides with decelerated thinning of Scandinavian glaciers as well. And taken together, they suggest that this slowdown in mass loss from these two regions, in addition to peripheral glaciers in East Greenland, define a regional pattern that they refer to as the North Atlantic anomaly. I also wanted to point out that despite the regional increase in snowfall in East Greenland that we observe in the most recent decade, we do find a high rate of frontal change in the southeastern glaciers between 2010 and 2021. And this suggests that the increase in accumulation in East Greenland wasn't sufficient to impede the retreat of glaciers and ice caps there. And we think this could be in part because of differing hypsometry between glaciers in the Northeast region and the Southeast region. So the majority of the area of the Southeastern glaciers are located at pretty low elevations, whereas the majority of the area of the Northeastern glaciers are at much higher elevations. So I'll just start to wrap up here. So our study provided the first comprehensive picture of glacier retreat across all of Greenland's key regions over a century timescale. And this allowed us to contextualize the Greenland-wide magnitude of 21st century retreat within a century-long timescale for the first time. And to really get at that question I introduced in the beginning of the talk, how unusual are these recent rapid changes that we're observing in Greenland's glaciers? So a few take-homes from our study. So first, we observe a notable shift into accelerated retreat over the last 2 decades, and glaciers are now retreating at roughly twice the rate observed over the 20th century. And despite the wide range of climate zones and glacier characteristics across Greenland, we find that this recent acceleration is largely ubiquitous and occurring even amongst Earth's northernmost glaciers. Second, I think our work provides much enhanced confidence that recent changes are largely exceptional on this century timescale. So in other words, for most of our regions, we find that the rate of retreat that we observed in the 21st century is unprecedented when viewed within this lengthened century-long context. And we also point out that with continued rise in greenhouse gases and further warming, these already pretty exceptional rates of retreat are likely to be exceeded in coming decades. And third, our study also shows that these glaciers respond very quickly to climate shifts. So that also reinforces that our choices and how much we reduce our emissions matter and have significant consequences for Earth's glaciers, also underscoring the need for swift action to limit global temperature. And lastly, I think important in the context of this seminar, I think the loss of these smaller glaciers can also be thought of as an early warning system or a way to understand the climate pressure that we're placing on Greenland's central ice sheet, which holds enough water to raise global mean sea level by more than 20 feet. So I'll just wrap up here just by providing some links. So we did publish our paper open access, and we also wrote a research briefing, which is a new short format for communicating the main takeaways of the research project to a broader audience. And we also got some media attention from the New York Times, which was really exciting as a New Yorker myself. And our paper was presented along with another paper that Anders was involved with on Greenland's last remaining ice shelves in northern Greenland. So with that, I'll wrap up. I am looking for graduate students to join my lab. So please do get in touch if you're interested in this type of work. And thank you. I'll take any questions.
Great. So we had a question in the chat. Maybe we can start with that. And I can read it out.
Okay.
So Vivian says, could the difference in east-west glacier retreat also be related to differences in ocean water temperature near the glacier front? And are most of these glaciers marine terminating?
Yeah, thank you, Vivian, for your question. And that's a great question. So we did focus our study on land terminating glaciers only, but I have seen several studies recently suggest warming in the northern North Atlantic region. So I think that could definitely be also creating a moisture source for this increase in precipitation in eastern Greenland. And of course, sea ice change could also, I think, be part of that as well.
And I think Jeff is next.
Hi there. When you looked at the warming in the 1930s, which obviously is internal variability, did you see the growth of those glaciers that were treated?
Could you repeat that the last part of your question? I'm sorry.
So the glaciers which were treated in the 1930s, did they regrow in the 1940s and 50s?
Okay. I think some of them, yes, but overall we do just see retreat through the 30s to the 70s. You could see that some regions, the retreat here is very, very low. So depending on the glacier, some would have readvanced and some would have continued to retreat. But overall, we're seeing retreat during those periods.
Thanks.
And then we have Luke.
Hi, hey Laura, great talk. I have a question. So you've basically showed that the retreat here is largely related to changes in surface mass balance. And I'm wondering if you can, like, you've mapped out the retreat, the terminus positions of these glaciers. Can you glean any information about like changes in surface hydrology or the elevation of the snow line? Can you like get any like direct indicators of changing SMB from the photographs?
Yeah, that's a great question and something that I've been thinking about. I think you can probably map snowline position because these are pretty high resolution photographs. I think the main I guess, hindrance is just the time it takes to get these photos in a place where you can measure anything on them. So, we could do that with the imagery that's already in digital form, but I think it would be like a massive undertaking to do that for many more glaciers around Greenland. But that is a great point and something that, yeah, I've been considering for future work. Yeah.
Thanks.
Do you have any other questions? Well, if not, I guess we can stop there. Oh, another one from Jeff.
If the glaciers have been in constant retreat, that implies that they're intrinsically unstable in the climate system, because obviously there have been colder periods since the 1930s, and that therefore they're just remnants of the last ice age.
I think that the dramatic increase in retreat in the beginning in the 20th century suggests that they are responding pretty quickly to climate changes. But of course, they're not in equilibrium with our current climate state. So if we stopped warming today, these glaciers would still retreat. And I think that disequilibrium is something that is not well quantified at the moment.
Okay, so guess we can stop there. So no more questions. So thanks again, Laura.
Thank you.